Right? So for polyprotic acids, the titration of, this is sulfurous acid with sodium hydroxide, so we have a weak acid. The only strong polyprotic acid that we have is sulfuric, H2SO4, but H2SO3 is a weak acid. And the interesting thing here that happens is if your pKa's are far enough apart, you have two separate equivalence points. So this first equivalence point means that you've just taken H2SO3 and converted it all into HSO3 minus. And so once you get past that first equivalence point, that's when you start to take away that second hydrogen. So they're spread far enough apart, it holds onto its second hydrogen strong enough, but will lose all of the first hydrogens up through an equivalence point. So you'll get one spike in pH, and then it'll level out for a little bit, and then it'll spike again. Because it happens like this, the amount of base that you have to add to get to the first equivalence point, right? So if we take all of our H2SO3 and we remove all of those, we remove one proton from all of those, that's how much it takes us to get to the first equivalence point. We still have the same amount of sort of SO3 ions. Now they all just have one proton left. So it's going to take exactly the same amount of base to remove the second proton and get to the second equivalence point. So the volume of base from the start of the titration to the first equivalence point is going to be the same as from the first equivalence point to the second equivalence point. So you essentially have to remove all of the proton, or you have to remove one proton on all of them before you can remove a second proton on any of them. And then you have to remove all those protons again. So volumes end up being identical. And I think for pretty much every weak base, that's the case. At least all the ones that we cover in this class, all of their pKa 1s and pKa 2s are sufficiently far apart that this will be the case. So for this question, is a little bit tricky. So we have three different titrations. In one of them, we have a monoprotic weak acid. The other one, we have a diprotic weak acid. And the third one, we have a strong acid. And we're titrating the same concentration of each of them with the same concentration of sodium hydroxide. So, keeping that in mind, which of these statements is most likely to be true? All three titrations have the same initial pH. All three titrations have the same pH at their first equivalence point. Or all three titrations require the same volume of sodium hydroxide to reach their first equivalence points. So, I'm not going to lie, I had to really think through this one and go back to the book because there's a lot of stuff going on here. So all of these questions, well, two of the questions are about equivalence points, and the last one is about the initial pH. So we don't know what these acids are, right? But we have two weak acids and we have one strong acid. So it's very unlikely that our initial pH is going to be the same. That one's safe to say, right? Because for the weak acids, we have to do an ice table. For the strong acid, it's just going to be whatever the concentration of the acid added is. For these other two, then, we have to consider what is an equivalence point? What does that mean? Right, so when we get to the equivalence point for any titration, what does that mean that we've done? What is equivalent? The acid and base concentrations are the same. Yeah. So if the concentration of our acids and all of these is the same, that means we have the same number of acid molecules floating around in the solution. So to get to the equivalence point, it's going to require the same amount of base, as long as the bases are all the same concentration, to reach that first equivalence point. Because it's like saying, all right, each of these has 100 acid molecules. So each of those is also going to require 100 base molecules to get to the first equivalence point. And again, the pH at equivalence points, because we have two of them that are weak acids, is going to be different than that strong acid. So the only one that can be true is C, because equivalence point is all about putting the same number of moles of acid as moles of base inside the solution. Okay. We're almost done with acids and bases. Briefly going to talk about indicators, and then we're going to move into like solubility stuff, which is like, well, we'll say more about that when we get there. So in here we have used some indicators in previous labs. In the most recent labs we used the pH meters, which are really nice. But when you're using an indicator, this is not something that you've probably had to think about before in any lab. You have to pick an indicator that's going to actually change color when you want it to change color or at your equivalence point. So we got to know stuff about indicators and how to choose an indicator, because there are lots of them spanning the entire range of pHs. So indicators are actually weak organic acids. So they are weak acids. So when we're using these, they can, if you add too much of the indicator, have an effect on the balance and your pH curve, right? Because if you add too much of the weak acid, now you're also titrating the weak acid that is the indicator along with whatever your unknown is or your other analyte is. So you only use tiny, tiny amounts, and they all form bright enough colors that you can see them. So this is the structure for phenolphthalein, fun molecule. So in acidic conditions, it's colorless, but when you break this ring system here open, it suddenly has color. So how do you pick an indicator? Well, the important thing to know about these indicators, because they are weak acids, their effective range is actually similar to, for our buffers, what a buffer's effective range is. Because we're switching from maybe the deprotonated form to the protonated form, or vice versa. And so, I'm not a huge fan of the way this is worded, but indicators change color within a range of 2 pH units centered at pKa. So it'll change colors if we have pKa at starting at pKa -1, going to pKa, and then it'll continue to change color until you get to pKa +1, or where the pH is the pKa -1, pKa, and pKa +1. So if you're going to pick an indicator, then you want to pick something that's going to line up with whatever titration you're doing. And that's why phenolphthalein is used for the strong acid, strong base titration. So phenolphthalein is down here, and its range is given sort of vaguely, but its pKa is actually somewhere above 9, right? Because we know the pKa is going to be in the middle of that color changing range. And then it'll start to change colors really just above a pH of 8. So it makes it a good indicator for that solution. You could go and look at for the titrations that we did or for the titration we did, you could pick an indicator now from this list of ones that would change colors, so you didn't have to use a pH probe for that diprotic acid. Some of these are really, really cool. So like, actually, do we have? Oh, I thought there was a picture of one. Some of these will change, like bromocressyl green. Actually goes from a yellow to a green and then a blue color. I don't know what colors show up in here. So that's kind of all we're going to say about indicators. Graciously simple. Now we're going to, let Let me move this so it's not covering stuff. So when you get into higher levels of chemistry and find out that everything you've learned so far is oversimplified and useless, it's kind of what we're doing now, because you learn solubility rules, and those are fine for like general stuff. But now that we've done all of this stuff with equilibrium, we could talk about degrees of solubility. So really, anything that you put into water, and I think that was the quote at the beginning of this chapter, anything that you put into water is going to dissolve even a little bit. So there will always be some of it that dissolves, and now we're going to talk about sort of the chemistry around, and really the math around how to calculate how much dissolves. And these are nice. These are still equilibrium problems, but because it's a solid dissolving, we've essentially eliminated half of the equilibrium. So we're only talking about the things, the ions in solution, and not the solid, because it's not part of the equilibrium expression. And so this is going to involve sort of a lot of tricks and concepts of the previous equilibrium stuff that we've done. So dissolution is an equilibrium. You put some solid in, it starts to dissolve. And if it's only slightly soluble, it's going to stop at some point. We have a value called KSP, right? That's the equilibrium constant for anything dissolving in water. But it's not always the most useful measure. Sometimes it's more useful to think about not this KSP value, but instead how many ions it's actually going to produce when you add a certain amount to water. So that's what molar solubility is. When you add it into a solution, when you add a solid into a solution, what is the concentration of the ions produced? All of the ions together. We'll see specific examples where that's especially useful. So K values are all unitless, and that's because they're all normalized. Molar solubility is in units of molarity, because what we're actually going to be calculating is these concentrations together. So for this calcium fluoride dissolving, we're going to calculate the total concentration of the calcium and the fluoride in the solution. So molar solubility is a quantity of the compound that dissolves in a certain amount of liquid. So using molarity, because moles per liter, it's going to be very useful, and we're going to use it for a lot of these calculations. So it is not the same as KSP. It's probably the most important thing to note here. Molar solubility and KSP are two different things. They're related, but they're different. Alrighty. So if we look at KSP and molar solubility for silver chloride, when you add a solution of silver chloride, right, we can create an ice table and say that when you first put that solid into the solution, it's going to dissolve, but how much? So we can calculate the molar solubility without even having any values to plug in for silver or chloride. And we use S here instead of X because we're calculating molar solubility, which is S. So we'll take this and use it just like we did all of our equilibrium stuff for like Ka, all of those other equilibrium constants. And so we're going to take KSP equals, and just for this equation, or for this reaction, it's going to be Ag plus Cl minus. And now we're just replacing the Ag plus concentration with S, and we're also replacing the Cl minus with S, because we're interested in not just one of the ions dissolving, but both of them at the same time. So this only works because the solid's not part of the equation. So our KSP here is going to be 1.77 times 10 to the negative 10 equals S times S, or S squared. So 1.77 times 10 to the negative 10 equals S squared. So if we take the square root of both sides, This is going to be 1.33 times 10 to the negative 5 equals S. And really, unlike K, this does have units of molarity. So that's our molar solubility. Easy enough, right? Always starts out easy. Okay, so there's this whole table here, actually, of KSPs. And see lots of different values. And I think it's going to be on the next slide. But just to get to this idea of why molar solubility is so useful. For silver chloride, when it dissolves, right, produces one silver, one chloride ion. So that's why we get KSP equals concentration of Ag times the concentration of Cl minus. For something like barium fluoride, now our KSP equation is going to be the concentration of barium 2 plus times the concentration of F minus squared. And so something like barium fluoride is actually producing a lot more ions in the solution per mole of barium fluoride that dissolves. So the reason that molar solubility is so useful is it takes this into account. When we put silver chloride, it doesn't produce as many ions. And especially when we have things that have competing ions, so producing the same ion in solution, that's going to matter. So lots of them there. Ah, yes, good. So iron hydroxide dissolving in water. We'll have our FeOH2, and that's our solid, in equilibrium with the iron 2 plus the 2 OH minus. So you'll probably skip ahead and see where this is going a little bit at least. But definitely, since this is the first one that we've done that has this, produces really 3 ions in solution. All right, these are going to start out as 0, and then this is going to be plus S. And then for our hydroxide, what is that going to be? Plus 2S. So of course then that's our change is plus S and plus 2S. At equilibrium we'll have S and we'll have 2S. So then KSP is equal to the concentration of iron 2 plus and OH minus squared. And so now we'll replace iron and hydroxide with S and 2S. So this will be S times, and it's real important to remember these parentheses. The 2S goes in parentheses, and both of those are squared. So not just the S that's squared, but the 2 is also squared. I guess I could write the KSP in now. So that's going to be, our KSP is 4.87 times 10 to the negative 17. And then this is going to be S times 4S squared, 4.87 times 10 to the negative 17. I ran out of space, so I'm going to move this. 4S cubed. So if you take 4.87 and divide it by 4.87, e to the negative 17, divide by 3, or divide by 4, sorry. And then take the third root, 2.3, what was 2.30 times 10 to the negative 6 molar equals S, or our molar solubility. So, quick tip for your calculator. Third root, let's say third root of KSP in here, is the same thing as KSP raised to the 1/3. Good. So molar solubility, pretty easy so far. Kind of really simplified equilibrium stuff. Now we're going to flip the script a little bit. We're given now the molar solubility of silver bromide is 7.3 times 10 to the negative 7 molar. Calculate KSP. So you start this out exactly the same way. We have silver bromide solid. And when it dissolves, get silver and bromide. And this one's pretty easy. So we can just, again, 0 plus S, S, and S. So KSP is equal to S squared. KSP is equal to 7.3 times 10 to the negative 7 squared. This almost feels like it's too easy. It's like, man, we eliminated half of the equilibrium expression. This is just, yeah, taking square roots, squaring things. The hardest thing at this point that you have to do is remember that if you get a 2s squared, that you need to square the 2 and the s. Okay, we could do more interesting things with these, though. So molar solubility and KSP are related, and I hinted at this already. But we have two compounds here, magnesium hydroxide, so it has 2 hydroxide ions, and iron carbonate. And if we look at just their KSPs, magnesium hydroxide has a KSP of 10 to the negative 13, where iron carbonate is 10 to the negative 11. So you might, by looking at this, think that the relative solubility of iron carbonate is going to be higher than the iron carbonate is going to be higher than the magnesium hydroxide. But the magnesium hydroxide actually produces more ions because for every magnesium hydroxide that dissolves, you get the magnesium and 2 hydroxides instead of just the iron and a single carbonate. And so the molar solubility is actually higher, 10 to the minus 5, than 10 to the minus 6 for iron carbonate. So especially when you have 2 solids that have different numbers of ions that are produced, you have to use molar solubilities to compare them. If they're the same, then KSP is going to tell you enough about which one's more soluble. So if we compare magnesium hydroxide to calcium fluoride instead, where both are producing 3 ions, then magnesium hydroxide is less soluble, and its molar solubility is smaller than that for calcium fluoride. And that's again because we multiply the concentration of the fluoride or the hydroxide by 4 and square it. So that's going to be important when we're talking about effects of common ions. It'll be more important later. This is the common ion effect, and this was actually one of the questions on, or related to one of the questions on the lab exam. So if you have calcium or fluoride added to the solution, just like when we had like 2 weak acids in a solution, the stronger acid is going to suppress the ionization of the weaker acid. In this case, if we have fluoride ions already in the solution, it's going to suppress the solubility of calcium fluoride. And in fact, you can use this as a method for getting more calcium fluoride to precipitate. So for the barium, I think it was barium chloride added to the barium chromate problem, adding more barium ions increases sort of that pressure to create barium chromate solid. So again, using Le Chatelier's principle, all of this other stuff that we've covered before, right? These are all the same principles. I want to be hesitant. I don't want to gloss over things, but I want to like emphasize like you've learned this stuff. You can keep applying these things to other areas. So, right, adding more fluoride, equilibrium shifts left. So when we go to calculate something like this, if we have or want to calculate even the molar solubility for calcium fluoride in a solution that's already got calcium ions, so calcium nitrate, we have to include that in our ice table, just like we would include it, just like we include previous hydroxide ions in a weak acid ice table. So we have calcium fluoride, again, dissolving, so Ca2 plus 2F minus. And now instead of starting out with 0 calcium ions, we're starting off with 0.25, 0 calcium ions, or molar calcium. And then 0 fluoride. So that's our initial. We don't need this. So our change is still going to be plus S for calcium, plus 2S for fluoride. And our equilibrium now is 0.25 plus S and 2S. And then we'll write our KSP, 1.46 times 10 to the negative 10 equals 0.250 plus S times 2S squared. You might be thinking, oh no, we have to do another quadratic equation. But in those, right, 2 weak acid problems, if there's already H3O plus in the solution, or if there are already calcium ions in solution, and our KSP here is really small, times 10 to the negative 10, what do you think that's going to do to S, and how it's going to, or this S plus S changing the 0.25? It's probably so small that it doesn't even matter, right? So we can just make that small s approximation. And making that approximation based on this knowledge that that's going to make our solution or our solid dissolve even less. And of course, doing so to avoid another quadratic equation. So now this is going to be 0.25 times what is going to be 4s squared. And 4 times 0.25 is going to be 1. So this is just going to be s squared. Because this will be 4s squared times 0.25. So 1/4 times 4 is 1. So the square root of 1.46 e to the negative 10, 1.21 times 10 to the negative 5 molar equals S. Cool. Any questions so far? No? All good. All right, so building on the same idea, which of these solutions is going to be, or I guess in which solution is solid barium sulfate going to be most soluble? Thinking about common ion effect, right? So if we have barium sulfate, when it dissolves, is going to be Ba2 plus and SO42 minus ions. So A, right, has barium ions in it. B has sulfate ions in it. Both of those are common ions to barium sulfate. So those will suppress that solubility. But C doesn't have any common ions. So because there's nothing already in the solution that matches the ions that would be produced by barium sulfate, it will be soluble, or most soluble in that solution. Still not going to be very soluble. Cool. So what about pH? Well, we do end up with another sort of Le Chatelier's principle situation, and one that is conveniently similar to another problem-ish on the lab exam. So we can use pH and manipulate pH, and it does have some effect on the solubility of various solutions, especially things containing hydroxide. So for magnesium hydroxide, if the pH is high, meaning we have a basic solution, the common ion effect decreases the solubility, right? Because if we have a high pH, that means we have lots of hydroxide ions in solution, and those are part of sort of this dissolution solvation equation for magnesium hydroxide. So if that's high, that's going to shift the equilibrium to the left. But if we have a low pH, then when magnesium hydroxide dissolves, those hydroxide ions that are produced will react with available hydronium. And so the concentration of hydroxide will drop as those get produced, and it will increase the solubility of magnesium hydroxide. And so if you have a really, really low pH, then you have lots and lots of H plus ions. You can just suck up all of the hydroxide and completely make the magnesium hydroxide soluble. So for problems like this, we could do isotables. So in general, the solubility of an ionic compound with a strongly basic or weakly basic anion, something like hydroxide, sulfide, because that can make H2S, which is a gas, or carbonate, because carbonate can also be carbonic acid, and carbonic acid will break down into a gas in water. Those will have increased solubility as pH decreases. So if there's more H3O plus, then the anions that they produce will react, and they'll dissolve more readily. So we've talked about acid rain. Rainwater is naturally acidic because it has dissolved CO2 in it, and that can dissolve limestone. And then as that acidic water is flowing into the ground, through the ground, it will get into underground caverns. Then that dripping water, when it's saturated with all that calcium carbonate, will then deposit that calcium carbonate into stalactites. and stalagmites, which is kind of neat. So which of these compounds would you expect to be more soluble in acid than in base? We have iron carbonate, and we have lead 3 bromide. So if we were to look at the dissolution products, and so if this dissolves, it's going to be iron 2 plus and CO3 2 minus. And if the lead 3 bromide dissolves, it's going to be Pb3 plus 3 Br minus. I know this was a bit of a pain point in the acid-base exam, that identifying whether or not anions or cations will make solutions acidic or basic, specifically here looking at the anions. So bromide would be the anion from a strong acid, which means that it's pH neutral. Strong acids, conjugate base is going to be pH neutral. But carbonate is the conjugate base of a weak acid. So if it's the conjugate base of a weak acid, how would that interact with acid or base in solution? So let's assume that there's lots of acid. So we're in an acidic solution. What is that going to do with carbonate? So how would carbonate, being the conjugate base of a weak acid, react with H plus in the solution? What's that going to do? Become more. It's going to become more acidic?
Less acidic.
Yes. Is carbonate going to pick up hydrogens? So if it's picking up hydrogens, we get HCO3 minus plus H2O. So it's decreasing. So it's reacting with, so if we have a high concentration of H3O plus, that's going to push this equilibrium over. It's going to use up that carbonate, and then even the HCO3 minus will also react with H3O plus and make H2CO3. And so that'll further decrease the amount of carbonate in the solution. So is that going to make iron carbonate more or less soluble in an acidic solution? If the carbonate ion concentration is decreasing. More soluble. Thank you for answering questions. If you guys are worried about being picked up by this microphone for the YouTube videos, it doesn't pick up any of your guys' voices at all. So you can answer stuff and nobody will ever know who you were. And there's only 7 of us here today. I mean, come on. That's fine. This is like the ideal situation, because then you can say stuff. It's like, all right, everybody here's in the same boat. Nobody said anything for like a full minute, so. No judgment. Okay, so yes, if we decrease the carbonate solution because it's reacting with, and it wants to react with the H+, because a weak acid doesn't ionize very much, which means that if it is completely ionized. It wants to pick up hydrogens to go back the other way. So it decreases our carbonate, and this will shift that way. So iron carbonate is more soluble in acid or in an acidic solution. Lead bromide, not going to be affected because bromide doesn't care about H+. In fact, right, that's why hydrobromic acid, when you add it to water, it gives up all those hydrogens immediately. It doesn't care about them at all. Carbonate loves its hydrogens. So again, comes down to being a Le Chatelier's principle problem. Okay, so another aspect of precipitation. And again, dredging up this idea of Q. So Q is something that we had way at the beginning of this, well, actually way back in equilibrium before acids and bases. Right? So Q is really an indicator of where we are relative to K. And so for K, you can only calculate K for equilibrium conditions, but Q is the one you calculate anywhere. And if it's larger than K, then you need to decrease your products to get back to Q. If it's smaller than K, or sorry, if Q is larger than K, then you have to decrease to get back to K. And then if Q is smaller than K, you have to increase your products. You'll make more products until you get to where K is again. So it kind of is an indicator of where in a reaction equilibrium you are. And then you can know, because of that, that you're going to want to, or your reaction is going to want to, get to K. So it'll move until those are the same. For KSP, we can calculate Q. And again, it's somewhat simplified because we don't have the bottom half. There's no reactant side of the calculation for Q. So it's just based on the ions that get produced in the solution. So KSP is the value of the product at equilibrium only. And then there's all these things that I already said about Q. Specifically for solutions, though, if Q is smaller than K, then it's undersaturated, so more can dissolve. If Q is equal to K, then it's saturated, and you won't dissolve any more. And the really fun one is if you can get Q larger than K, then you're supersaturated. Fun things happen when you have a supersaturated solution, because with just a little bit of shock, it will all crystallize at the same time. I should have had Andy bring out the sodium acetate. She has some bottles of concentrated sodium acetate, and it's very easy to supersaturate by heating. Similar to this, but not entirely related, is you can supercool things, so below their freezing point. This might have happened to you, like the one you see all the time is Coke bottles. So if you have like a Coke, you put it in the freezer. Sometimes you pull it out, and it's still liquid. And then you can either smack it on the table or just open it, and it will all freeze at the same time into a very nice slushy consistency. Gatorade will sometimes do it. I need to figure out what the specifics are for making it happen every time because it's fun. So we can use Q then for our solubility stuff to tell if we're going to be able to dissolve more product, or if we are saturated, or if it's a supersaturated solution. And generally, when you're calculating this, if Q is larger than K, then you're going to be forming precipitate. If Q is equal to K, then adding any more will cause it to precipitate. Okay, so we're going to use this in some reactions to figure out the precipitation point. So a solution containing lead nitrate is mixed with one containing sodium bromide to form a solution that is 0.06 molar in lead nitrate and 0.0158 molar sodium bromide. Does a precipitate form in the newly mixed solution? Conveniently here, it's given us that potassium bromide's KSP is 4.67, so that's the solid that we're going to be looking for. So to calculate K, or to calculate Q, our Q expression looks exactly the same as K. So this is going to be the concentration of lead, 2 plus, times the concentration of Br minus squared. The Br minus is squared because there's 2 of them in lead bromide, and so if we dissolve it, then it'll be Pb2 plus 2 Br minus. Okay, so looking at these, another place to sort of be careful on these kind of problems is that here, right, we get 1 lead per lead nitrate. That's good. So that means we can use the concentration as it's given, 0.0600 molar. That's lead. And then for sodium bromide, that's also 1 bromide per every sodium bromide. If that number is different, if it was something like magnesium bromide, just trying to think if that was soluble or not. If it was magnesium bromide, then we'd get 2 bromide ions for every magnesium bromide in that solution. I don't know if we have any examples of that, but so this, because there's 1 bromide in sodium bromide, this is the concentration also of bromide. So we can just write that in squared. So our Q is going to be 0.06 times 0.0158 squared. And Q is equal to 1.4, I guess 1.5, rounds up to 50, times 10 to the negative 5. So is Q larger than K? Yes. So because Q is greater than K, a precipitate will form. Cool. All right, so calculating Q, same way that you calculate K, just got to make sure that you're using the correct concentrations for each of those species. So selective precipitation is, actually, are we doing that on Wednesday or Thursday? Might be doing a lab with this on Thursday, but it's kind of related to the qualitative analysis stuff, which is some of it's laid out over here in the hood, where you're going to be using, well, that's mostly using different reagents to selectively precipitate things. Also, if you have 2 compounds that you know are in the solution, and you can measure out very carefully the concentrations and of the reagents that you're adding, you can sort of hit the precipitation point for one of the compounds by adding a common ion, and then not hit a precipitation point for something else in the solution, even though it'll form a precipitate with the same ion. And so that's what this selective precipitation is that we're going to talk about right now. And this is all based on the relationship between Q and KSP values for different compounds. Key things here is that reagents are chosen based on KSP values. So if you're trying to precipitate 2 things, just picking random examples here, like lead 2 and iron 2. I think iron 2 forms a solid with chloride. You want to pick something that's going to have a KSP value with a factor of at least, or a difference in 10 to the positive 3. Right? So 3 orders of magnitude different in solubility. And then we can compare Q and KSP to figure out how we get to precipitating just one thing. So if a solution contains equal concentrations of barium, lead, and calcium ions, if we add potassium sulfate, which cation precipitates first? So let me zoom this in. So we're looking at sulfate, solids, with calcium, barium, and lead. So here's lead 2 sulfate. There's barium sulfate. And there's calcium sulfate. First thing to check on a problem like this, do they each have or produce the same number of ions? It's like calcium sulfate, right? Barium sulfate, lead sulfate, they're all just producing themselves the cation plus the 1 sulfate. So we don't need to worry about calculating molar solubilities. If one of those produced a different number of ions, then we'd have to calculate a molar solubility instead to do this comparison. So since that's not the case, we can just look for whatever has the lowest KSP. So the thing that's least soluble will precipitate first, and that is, what was it? Calcium sulfate, 10 to the minus 5. 10 to the minus 10 for barium sulfate. The smallest one. Yeah, barium sulfate. So yeah, smallest KSP is going to dissolve first, or going to form a precipitate first. And then you can imagine that if you continued to add more potassium sulfate, if all of it is precipitating as barium sulfate first, then none of those sulfate ions are actually hanging out in the solution to precipitate with the other things. Right? So it's kind of like a titration, but you're creating a solid instead of neutralizing pH. So that's kind of the relationship here. So if we have magnesium, calcium ions present in the solution, and we know they can be separated by selective precipitation with potassium hydroxide, what minimum hydroxide concentration triggers the precipitation of the magnesium 2+ ion? So a couple things at play here. One of them is that we know that Q, right, when Q is equal to K, is this one? That's the next one. Yeah. Okay, so we know that we have the KSPs, and so we can look at our magnesium ion and its KSP, right? That's times 10 to the negative 13 versus times 10 to the negative 6. So magnesium is definitely going to be precipitating first. And this calculation is actually just going to be 2.06 times 10 to the minus 13 equals the magnesium concentration, or I'll write this, Mg2+ times OH minus squared. All right, so it's just our KSP calculation or equation. And so our concentration of magnesium and we could really replace hydroxide here with any variable. I'm just going to leave it as OH minus. So we can take 2.06, 6 times 10 to the negative 13 divided by 0.025, and then take the square root of that. So 2.87 times 10 to the minus 6 molar equals concentration of OH minus. All right, so this one stays pretty simple, and then we can go on and calculate how much it would take to precipitate the calcium. Still pretty simple. Still pretty much just writing down the KSP equation, plugging a few numbers in. This next one is a little bit trickier. And not in the least bit because the question stem is so long and contains two parts. So we have a solution that has lead and it has silver, given the concentrations. A, first part of this, if selective precipitation is to be used to achieve, words. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? Ugh. That's a very poorly worded sentence. So which of these ions precipitates first? Huh? Silver chloride? Probably. What's the difference between this problem and the majority of the other problems that we've done? It has to do with numbers of ions. Lead chloride has 2 chlorides. So we do need to calculate molar solubilities. And we know, based on the previous problems that we've done, that we can calculate the molar solubility. So I'm going to do lead chloride. This is going to be 1.17 times 10 to the minus 5 equals, this is going to end up being 4s cubed. Because we're going to do an ice table, and it's going to be plus s, and it's going to be plus 2s, and the plus 2s is squared. And then we'll take this and we'll say 1.17 e to the minus 5 divided by 4. And then the cube root. So molar solubility is going to be 1.43 times 10 to the minus 2. And a similar thing we do with silver. But it's a little bit simpler because there's only the 2 ions, so it's just s squared. So 1.77 e to the minus 10 squared, not squared, square root. This is 1.33 times 10 to the minus 5. And oh, would you look at that? Silver chloride is still less soluble. Okay, so we've identified silver chloride is going to precipitate first. How do we calculate how much sodium chloride we have to add, or the minimum concentration of sodium chloride that we need to have? Not even how much do we need to add. How, oh how, do we find the answer? Take a stab. What do you think? Okay, all right. So, what concentration of sodium chloride do we need to make silver chloride start to precipitate? This one?
Yeah.
Almost. Almost. So we needed molar solubility to be able to compare the two, because one produces 2 ions, the other one doesn't. Now we can just use KSP. Yeah, KSP equals the concentration of silver and the concentration of Cl minus. Yeah. Once again, the only brave soul. Okay, so this is for silver, so we're going to use 1.77 times 10 to the negative 10. And we know what our silver concentration is, 0.025 molar. And we want to know what the chloride concentration is. So 1.77 e to the negative 10 divided by 0.025. So we only need 7.0, well, I guess, no, why are the sig figs up there like that? We're going to say 7.08 times 10 to the negative 9 molar Cl minus. And kind of what we're doing here is we're kind of based on the ideas of Q and K. So right now our Q, because we don't have any chloride, Q is 0. So we need to make Q larger. Well, how much do we need to make Q larger by? Well, since we know, and this number for silver is fixed, we just need to figure out what we need to multiply the concentration of silver by to make it equal to K. Unfortunately, that sets up as a very neat little equation. So now the question is, that answered A. So I'm going to write this like this, A. What is the concentration of each ion left in solution at the point where the second ion begins to precipitate? So how can we figure out how much chloride we need to precipitate lead? It's almost exactly the same thing we just did. Someone new? So we use this to calculate it for silver. So what do we use for lead? The KSP for lead. So KSP for lead is going to be Pb2 plus and Cl minus squared. Because again, we know what KSP is, we know what the concentration of lead is, and so we can figure out what the concentration of the chloride ion is. So 1.17 times 10 to the minus 5 equals 0.085 times whatever Cl minus is going to be squared. I don't know why I put so many parentheses. I put a $1 for times. Try and scooch this. So 1.17 e to the negative 5 divided by 0.085, and then the square root of that. So this is going to be 1.17 times 10 to the minus 2 molar equals Cl minus. So that's how much chloride we would have to add to get all the way up until, wow, I said that really weird, up until the very point where lead would start to precipitate. So that's K is equal to Q. It's right on the brink, right on the precipice. If we had any more chloride ions, lead starts to precipitate. And the trick here is now we want to know what silver is going to be. And so we go back now to the KSP equation for silver. KSP for silver, so maybe I should like section this. That's A. Now we're working on B. So we needed to figure this out because it says, right, what is the concentration of each ion left in the solution at the point where the second ion begins to precipitate? So this is where the second ion begins to precipitate, that concentration of Cl minus. And now because even if we have all of this Cl minus and we've almost entirely precipitated out all of the silver, there is still a tiny amount that's going to stay soluble in the solution. Very, very tiny amount, but a very tiny amount. Some of it nevertheless. So we take our KSP for silver again. Actually, I don't think I have this. Well, I'll write it real small. Let me put another line in here. We're going to have to zoom. So our KSP for silver again, KSP equals Ag plus Co minus. And now we're not looking for chloride, but we wanted to look for how much silver is left over in the solution. So we type in, write in this KSP, 1.77 times 10 to the negative 10 equals Ag plus times the chloride concentration, but now the chloride concentration at the point where silver or lead precipitates. So 1.17 times 10 to the minus 2 molar. So this is going to be 1.17 E to the negative 10 divided by 1.77 E to the negative 10 divided by 1.17 E to the negative 2. So there's going to be 1.51 times 10 to the negative 8 molar Ag plus left in the solution. So now, the slightly tricky question, how much lead is still in the solution? We don't have to calculate anything. I know it says it in the top right corner. Now it doesn't. How much lead precipitated? Well, we went right up to the point before it precipitates. Subtract out what? Oh, like the Cl minus concentration? So this, right, when we set this up, this was the KSP, right, KSP, the concentration of lead. And we're kind of trying to find like what is the equilibrium when we have this much lead, how much chloride would we have to be at equilibrium here? So saying KSP is where we want to be, we're going to that point. So this times this equals, well actually, I mean this squared times the lead concentration equals KSP, which is the equilibrium. And because we're right at that point and we haven't added any chloride to go past it, all of the lead is still in solution because none of it has precipitated left, which is why the answer up in the corner is the same as what we started with. So the answer for B Okay. Some of the stuff here to go through real quickly. That's the last of the calculations we're going to do tonight. I'll put us maybe a little bit behind, but there's more stuff to calculate at the very end. This is the section, though, that's about the qualitative chemical analysis. Right, so this is all about finding the kinds of ions that are in the solution and doing that by using reagents that will selectively precipitate, different type of selective precipitation that we were just talking about. But yeah, so it's qualitative. So you're trying to identify the qualities about the solution, not identifying the quantity or the amount of things in the solution. So also kind of called wet chemistry. This has, largely been replaced by other instrumentation that's faster and easier and also quantitative. ICP-MS is one that comes to mind, which is inductively coupled plasma. So you take an analyte sample and you inject it into a plasma, and as it's being obliterated by the plasma, it will create ions of especially metals, which is mostly what we're talking about here. And so you can detect those individual ions and determine what's in a sample like that, rather than having to get enough of it that you can like mix it and add different things to the solution. This is still an important skill to know. And it's going to be the key to sort of the qualitative analysis stuff. So the idea is that we have a sample mixture. It's got a bunch of stuff in it. And we want to remove things one at a time as much as possible. And so after each time we add something, so we got cations A, B, and C, we add our first precipitating agent, and that drops one of these down to the bottom of the test tube. And then you decant your liquid. Now it's got everything minus what you precipitated. Add another precipitating agent, that stays on the bottom. Pour over the liquid. And then either you have something in there that maybe you know that there's 3 possible things, and so you eliminate 2 and you know that the last one's remaining, or you could do another precipitation to make sure that you do know what is in that solution. And I think part of the key here is you don't need to get all of the liquid out of this first test tube and into the second one. Because what you really, really, really don't want is any of the solid to go over with it. Because if some of the solid goes over with it, it might interfere in your next precipitation or in the one after that. So you take as much solution as you can while being absolutely sure that none of the solid came over. Because that can really throw things off. Oh, of course, this is going to look like garbage on this projector. Okay. So here is the holy grail of flowcharts for this kind of thing. These are all in the order that you would want to do them to separate out the individual ions, because doing them in this order means that you don't precipitate out something or co-precipitate things that are going to interfere. I'm not sure I'm quite saying this the way that I want to. Is the idea in my head. Sometimes if you, I'm lacking the words to verbalize this right now. But we're going to walk through sort of these steps, these groups, right? So I'm going to call this, I believe, is group 1, group 2, group 3. So the first group are the insoluble chlorides. And some of the logic is here, right? So most chlorides are soluble. So that's what makes this first one a nice one to do. But if you have silver, lead, or mercury, they will form insoluble chlorides. So by adding hydrochloric acid at the beginning, the hydrochloric acid serves a purpose as well, instead of adding sodium chloride, because you could add sodium chloride, but the hydrochloric acid serves a purpose. We'll get to in the next slide. So that's going to separate out these 3 from the solution. So you got your sort of master solution, you add some hydrochloric acid, and you got to precipitate. So you know that you had either lead, silver, or mercury. So you separate those solids from the liquid by decanting. and move on to the next group. So these are acid-insoluble sulfides. So, right, we added hydrochloric acid that acidified the whole solution so that we could look at these sulfides next. Because the concentration of sulfide is pH dependent. So at a low pH, high H plus concentration, you're actually going to have a very low sulfide concentration. And then only your most insoluble metal sulfides precipitate. So this is kind of like the idea with the selective precipitation that we just did. Right? If we can add just enough sulfide to precipitate these more easily precipitated solids, then we can avoid the other ones that are going to be harder to precipitate. It sort of gives us another layer of separation in our experiment. So mercury 2, before we had mercury, it's actually mercury 1 plus. I should go back up to this, right? So this is mercury, there's 2 mercuries, each of them has a 1 plus. It's a weird one. So here's straight up mercury 2, cadmium, bismuth, copper, tin, arsenic, lead, and antimony. So those can all be separated with this sulfide at a low pH. Next step then is you add a base. So you add an additional base, or you add base and hydrosulfuric acid. And so then now we've got the less or the more soluble sulfides. Right? Removed all the other sulfides. Now it's all the things that are going to exist or that are going to precipitate when there's a lot of sulfide around, because we added base to get more sulfide. So things like iron, cobalt, zinc, manganese, nickel. And then you can also get, if you add even more base, chromium, iron 3, and aluminum 3. Then moving on to group 4, now you've got only alkali and alkaline earth metal ions. So you should have removed everything else. And then you can add phosphate, and that ammonium phosphate will remove your magnesium, calcium, and barium. Then finally, we're left with those somewhat awkward ions of sodium, lithium, and ammonium, which don't form any solids at all. So ammonium and lithium sodium and lithium can be differentiated by adding, or by a flame test. So sodium's going to make a orange flame, potassium will make a light blue flame. And really, ammonium, you can smell. You're going to get that ammonia smell. And so you can probably identify it like that, even though it doesn't say that officially on these slides. Okay. So it's kind of the general overview on those. It is the overarching idea. And this is complex ion equilibria, which I'm going to tack this onto the beginning of next lecture, because we're going to do more of that.